In this video, we are going to continue to talk about the Diels-Alder reaction. Specifically, we are going to be focusing on what's happening at the level of the diene and the dienophile. And we're going to start talking about, specifically at this time, about the dienophile. Understand that the Diels-Alder reaction is going to have stereospecificity, and that is going to be depending at this level on what is going to be present at the level of the dienophile. As you can see, if you have a dienophile that is E or Z, that is going to reflect at the level of the product of the reaction. So as you can see in the first box, we have a Z dienophile. And when we look at the product of the reaction, we are going to be forming a single product that now the two substituents that it is in that dienophile are going to be cis, both pointing up in the reaction. Understand that we only have one product of the reaction because the product that is formed is going to be meso, so it's going to superimpose to its mirror image. Now, if we have an E configuration on the dienophile, understand that then, when it comes to the product of the reaction, that cyclic alkene that is formed from the Diels-Alder reaction is going to have its enantiomer also forming. Now, dienophiles are not restricted to only being E or Z alkenes. We can also have alkynes as a dienophile. And when an alkyne is functioning as a dienophile, as you can see, we are going to have specifically two alkene molecules forming in the product. Okay. Now, remember that when we were doing these, or when we introduced the idea of dienes actually had two conformations. We could have S-cis dienes, or we could have S-trans dienes. Now, in the Diels-Alder reaction, that can only happen if our diene is going to be in the S-cis conformation. S-trans diene will not be undergoing specifically a Diels-Alder reaction. So understand that if you have a particular diene that is trapped as an S-trans conformation, it is not going to be undergoing a Diels-Alder reaction. So as you can see in the example that we have on the top, we have a diene that it is trapped at the S-trans conformation. Now, because the carbon atoms in the diene, specifically carbon 1 and carbon 4, are far apart, even if you put them in the presence of an alkene, it is not going to undergo the Diels-Alder reaction because of the separation of carbons 1 and 4 in the diene. Now, dienes that are locked into the S-cis conformation will undergo the Diels-Alder reaction readily. So as you can see here in the bottom of the slide, we have the example in which we have cyclopentadiene. And this cyclopentadiene is going to undergo the Diels-Alder reaction. Now, because cyclopentadiene specifically, it is cyclic in the beginning. When we perform the Diels-Alder reaction, understand that what we are going to be forming here is a bicyclic product. So, if I label the atoms, this carbon atom is the one that it is here. So understand that if you start with a diene that it is cyclic, we are going to be forming what is called a bridge. At this reaction, okay? And remember, because here we have an E configuration, specifically in our dienophile, that's why you're going to be forming the first molecule plus its enantiomer. Now, understand that cyclopentadiene is actually a very special molecule because it is so reactive towards the Diels-Alder reaction that it will react with itself without any specific amount of heat added to the reaction, so at room temperature, and it's going to form a dimer. And as you can see, here is the product of when cyclopentadiene reacts with itself. Now, another thing that we need to establish when it comes to the bicyclic systems, okay, is that the addition of specifically the groups that we have in terms of the dienophiles are going to be forming two products, okay? They're going to be forming the endo product and the exo product. Now, understand that the difference between the endo and the exo products is going to be how are they going to be aligned with the particular bridge that we have available in the molecule that it formed. Okay, so if we look at the molecule that it is in the bottom, okay, which will be the product for the following bicyclic reaction, understand that when we are looking at the product of the reaction, remember, we have a bridge in which we have that single carbon that is pointing at the top of the molecule, okay? That is there being pointed at by the gray words. Now, if we look at the bridge that has the two carbon atoms, because that is the larger bridge, when we look at the endo versus the exo, I want to illustrate it by highlighting the bonds. The endo product is going to be syn to the larger bridge. So you can see if we actually focus, they're both pointing down. Now, if we compare that bond in the larger bridge, which I'm still going to highlight with a different color, and we compare it to the exo product, which as you can see is going to be pointing up, as I highlighted in that light brown color, the exo product is going to be anti to the larger bridge. Now, we need to talk about what is going to be more favorable, endo or exo product in these bicyclic systems. So, understand that the electron withdrawing group attached to the dienophile tend to occupy the endo position, okay? Most of the time. So that is going to be our major product. Often this endo product is the only product that it is observed in the reaction. Understand that the reasoning behind why the endo product is more favorable is because the endo transition state is going to favor a more favorable interaction between the withdrawing groups and the developing pi bond in the system. And as you can see here in the first figure, we have the transition state that is developing in between the diene and the dienophile. Okay, so because that favorable interaction between the developing pi bond in the electron withdrawing group, that's why the endo product is going to be more favorable. In the case of the exo transition state, it doesn't have a favorable interaction. As you can see, when it comes to what we need to form in terms of the cyclic system, okay, understand that there is a separation, okay, in between that electron withdrawing group and the pi bond that is going to be forming. So because that separation in terms of distance, and then they're too far apart, so there's no interaction. That's why exo is not going to be as favorable. If we look at it in terms of an energy diagram, and overall here we have the reaction coordinate and the potential energy for each one of these systems. Remember, Diels-Alder reactions happen with only one transition state. That's why we only have one hump. So in the energy diagram, when these two products are illustrated, even though the exo product, it appears to be lower in potential energy and might be suggested that it is more stable. The reason why the endo product is going to be actually favored in these conditions is because its transition state is going to be lower in energy and it forms faster. But we also explained how that transition state, it is also favorable when it's interacting with that electron withdrawing group that is present in the dienophile. Now, understand that only one regiochemical outcome, okay, is going to be happening if you have a diene or a dienophile, okay, that is symmetrical. So as you can see in the top example, which I'm going to label as number 1, we have a symmetrical diene. And in this case, because our diene is symmetrical, when we combine it with our dienophile, as you can see, we're only going to form one product. Now, if we have a symmetrical dienophile, and as you can see in the second example, we are going to have specifically an alkyne dienophile. Understand that in that system, we're also going to produce one product. Please remember to look earlier in this video to look at how many products we have, specifically depending on the dienophile that we have, if it's E or Z. Now, if the diene and the dienophile are both unsymmetrical, then you have two regioisometric products possible. So as you can see in the following example, we have a diene that has a substituent in it. And we have a dienophile that has the electron withdrawing group. As you can see here, we are going to have a major and minor product because what's going to happen is that these regioisomers are formed and they have a regioselectivity. So when we are trying to determine which one is the major product and which one is a minor product, just depending, as you can see, from the dienophile and the diene that we have, we need to consider the following. The major product of the Diels-Alder reaction can be predicted by considering the charge distribution of the reactants. So if we look at the diene that we had in the previous molecule and we look at that electron donating group, attached to our diene, then we can actually show a resonance structure in which we can actually see that the carbon atom in the corner of our diene is going to be negatively charged. Remember, in the previous example, our dienophile has an electron withdrawing group. And as you can see, we can write a resonance structure for the area of the aldehyde. In addition to that, once we create that, we can suggest another resonance structure in which the carbon-carbon double bond then goes and forms, okay, a double bond that is going to be closer to the oxygen that is negative, and then the carbon atom in the bottom is the one that gets positively charged. So considering the location of the partial charges and the attractive force, what's going to happen in the reaction overall is that now we can observe where specifically in the molecule we have that partial negative compared to the partial positive charge within our molecule. So what that means is that when we are trying to consider, if we draw now the arrows, this forms a double, the single bond, this forms a double bond, this is going to form specifically the other sigma bond, then we can see that this is the major product, okay? Because that partial negative charge is going to be attracted to that partial positive side in our dienophile. So the way that they're going to be reacting and forming that pi bond and the two sigma bonds is going to be as illustrated in the following slide. So just take the electrostatic forces that are going to be created into account when you're trying to determine what is going to be the major product of this reaction. As you can see, this alignment of the electrostatic forces, because it results in a lower energy transition state, then we can see that this product that we have written is going to be the major product that forms faster in the reaction. So make sure that you practice in section 16.18 in the textbook the regioselectivity that can occur in these type of reactions.